Hello everybody, welcome to the next video in the series of Physics at Home. In today's video, we're going to talk about momentum and collisions. Momentum is mass times velocity of an object, and when two objects collide, their momentum is conserved. This is true for three kinds of collisions: elastic, partially inelastic, and completely inelastic collision. In today's demonstration, we are going to concentrate on completely inelastic collision, wherein the objects after the collision they stick together and move as one. The two objects are the two cars. And to make sure that once they collide, they're going to stick together, what we have done is put a tape of Velcro. The rough Velcro is here and the soft Velcro is here. So the way it's going to work is there you go. So one car rolls down, we can time that the distance it covers, and then we also going to time that after the collision, how long does it take for these cars to travel, from this tape here to this book. Okay, so I measured the distance already. The ramp is 52 centimeters, and I'm going to place the car right at the bottom here, so that once this one comes down, as you can see, the rear wheels of this car, when they get down the ramp, is when this is going to collide with the second car. And then these two are going to travel together. Okay. Now the distance from here up to the book is about 35 centimeters or 0.35 meters. This distance, if you're trying to do this at home, make sure that it's a horizontal surface, and also there are no roughness here, so that these cars, they can have as little friction as possible on this horizontal surface. If the distance is too far, then, definitely friction will interfere. If it's too small, then you won't be able to time it. Okay? So, the ramp distance and the second distance after collision, those I already know. What we also need is the masses of the cars. This car here, before I started the video, this one I measured is about 33 grams. And this one here is about 37.5 grams. Okay. So the two distances and two masses is what you're going to need before you start the trial. Okay. And what you need to do is make sure that when you place this car here, the second car, make sure that this is aligned with the ramp, so that when this one comes down, they are gonna have a tail. This one is gonna get tailgated, and they're gonna stick together and move as straight as possible. If they collide and they turn, or go in some kind of crooked path, then we have to repeat the trial. Okay. So let's see. We need to time, and what I'm gonna do is I'm gonna start the watch. Okay, stopwatch, and when the car is released, and when this one collides here, I'm gonna say lap. Okay, so when I say lap, it has recorded the time it takes to go down the ramp, but it continues to measure the time, and when it hits here, I'm going to stop it, so that I would know the total time lapsed from beginning all the way here, so that the total time minus the first lap will give me the time for this distance. Okay, and then those two times we're going to see in the next section how we can use to verify the properties of completely inelastic collision. Okay. Let's see. Let's start here. 1, 2, 3, go. Oops, I think I did not do it. Hold on 1 second. One, two, three, go. Oh no, see, it turned, so I gotta redo it. It's aligned along the center. Start again. 1, 2, 3, go. Still give a bit of trouble. Let's see. Let's try one more time. One, two, three. Yeah. 1, 2, 3, go. Okay, So 0.66 and 1.23. Let's do it one more time. One, two, three, go. Okay, 0.7 and 1.23. Let's do a last turn. 1, 2, 3, go. Alright, 0.73 and 1.2. Okay, so I have the times for three trials. In the next section, we're going to see how do we verify the properties of the completely inelastic collision. Here we see the situation that we were, saw in the demonstration. There is a car A that starts at the inclined plane, and then it travels a distance d1. The mass of that car is 0.033 kilograms. Then it comes down, and then it's going to hit the car B. They're going to stick together and move over distance d2. Okay? And the mass of the B is 0.0375 kilograms. Okay? The distance 1 and distance 2 are here. Height was 0.14, but we don't really need it. It's just for a reference here. In the table here, we see 3 times for the distance 1. Those are the 3 trials. So those were the times when I start and lap, correct? So those are the 3 times. Average of the 3 is about this. And then time 2 is the time taken by both the cars to travel distance 2. And in my cell phone, it was giving me the total time from the beginning here all the way to the end here. So then I had to subtract the total time minus the time 1 to get time 2. So here we see 3 times for the distance 2, and the average is 0.527. What we need to understand here is that when it travels distance 1, the car is speeding up, right? It's accelerating. So if it is accelerating, we cannot really use the speed equals distance over time, because speed equals distance over time is applicable only when the speed is constant. So here, for the speeding up event, we're gonna use a kinematic equation, which is the x2 minus x1 half v1 plus v2 times t. We always say that initial position is 0, so x1 goes out, and since the car starts from rest, so the velocity 1 is 0 as well. So what we need is the speed of the car as it goes down this ramp. Okay, so reorganizing this, we get 2 times x2 is nothing but the distance 1, correct? x2 divided by t. Okay, so let's see how much that is. 2 times distance 1 is 0.52 divided by time 1 average was 0.707, and this turns out to be 1.471 meters per second. This is velocity 2. Okay, so this is the velocity or speed of A before collision. Yeah. Okay. Now let's think about when they collide. All right. So we said that after the collision, the momentum is conserved. So the momentum of A before collision plus momentum of B before collision is equals to momentum of A after the collision and momentum of B after the collision. So conservation of momentum applies to the system. Here our system is A and B together. And momentum is mass multiplied by velocity. So PA here would be mass of A times velocity of A. This is before the collision, right? And then mass of B times velocity of B before the collision. This is equals to mass of A, velocity of A after the collision, plus mass of B, velocity of B after the collision. Now we know before the collision, B was at rest. Yeah. So that means the mass B times velocity B before the collision, this term goes out the door. Not only that, but we know the velocity of A after and velocity of B after is the same because they're moving together. So we can just call it as a velocity after the collision. Okay. So mass of A times velocity A before the collision. Now we can factor the VA after and VB after because those are the same, right? So I'll take that out. So mass of A plus mass of B and then velocity after the collision, correct? Oops. After the collision. Okay. So we are interested in this value here, velocity after. Okay. So we know mass of A, we know velocity of A before collision, right? Which is this value right here. And then we know mass A and mass B as well. Okay. So we want to calculate this number. Okay. So this would then be mass of A times velocity of A before the collision divided by mass A plus mass B. This is equals to velocity after the collision. Yeah. So let's see how much that is. So mass of A is 0.033 times velocity of A before collision is 1.471 divided by mass A 0.033 plus mass B 0.0375. Right, so that comes out to 0.688 or 0.689. This is the velocity after the collision of both the objects, correct? Now we need another way to verify that indeed this is true. And this is where our distance 2 and the time 2 comes into play. In this horizontal section of the movement, we selected distance which was small enough, but manageable enough where we can time it. Small enough for the reason that we can safely say that the friction is not going to affect the motion of these two a whole lot. Okay, even though it's going to be there for sure. But given the distance is small, we can assume that this is a constant speed situation. So if the speed is constant, then we can calculate that speed just as a distance over time. So with that constant speed here, or the we can calculate that here. Constant speed is the distance 2 over time 2. So distance 2 was 0.35 and time 2 was 0.5. Oops. 0.527. So let's see how much is that. .664. All right, so this constant speed. So we have a speed here that physics tells us that momentum is conserved. So the velocity after the collision is 0.689, and the kinematics or the distance over time tells us this is going to be the speed 0.664. Now let's see how much is the difference between the two. That is our percent error. So which is the absolute value of the difference between the two? 0.689 minus 0.664, and we expected the constant speed to be close to 0.689, right? So this is the expected value here multiplied by 100, and that turns out to be 3.62. 3.60%. So the value of the velocity or speed that physics was telling us that could be after the collision, we get the same value if we time it over the distance that it covers. And this is how we can verify that indeed this was a completely inelastic, because the cars stuck together and the momentum of the system was conserved. Okay, all right. So I hope you enjoyed this video, and next week we are gonna look at moment of inertia.